Well, so welcome to the binary tree theory video. So today, you guys know the drill. We're going to be looking at the theory portion of the binary tree before we get into the code implementation in the next video. So, what's a binary tree? Well, so it's a data structure where each node has two kids, and they go on the left or the right. And so the topmost node's called the root, and then the nodes with no children are called leaves, right? So if you got, as you can see here, well, so like imagine a CEO position, right? Or like any kind of business where you've got, the CEO or whoever it is at the top, then, you've got VPs under them, and then they have employees, right? So in a structure like this, so you have 10 as the root, and then the left subtree is rooted at 5. And then, so this is your CEO, these are your VPs, and then these are your employees, right? And so, so that's the structure. Very, very, very easy to, comprehend. It's how we would think about a graph like this anyway. And so I included a little bit of sample from the code. And so in the code, we're going to have a binary tree made up of these tree nodes that contain values, right? So you're going to have a tree, and then that tree is going to be populated by nodes, and then within those nodes, you're going to have a value, and it's going to have a pointer. As you can see here, this is a box, right? So it's an optional pointer to the left or right node, right? So that's what is in that's what's in the major element, the nodes of the binary tree, right? And so why binary trees, right? So they're great at sorting and managing hierarchical data. They're used to solve problems like, search and sorting, because they have very efficient insert and delete functionalities. They're used in that. They're used in compression, Huffman trees, and then they're also used a lot in like decision trees and it's in compilers. I believe I mentioned it later on in the lesson. Expression trees. They're also used to implement expression trees in like compilers. And so Huffman trees, since I called those out, I wanted to kind of go into a little bit. So they're a type of binary tree. They're used for data compression, and so it analyzes the reoccurrence of information, and it uses shorter binary codes for more frequent and longer codes for less frequent. And so it basically counts how many times these characters appear in the input, and it builds a tree using the occurrences of those characters as a weight. Okay. So binary trees, they have particular attributes that you should know, right? So depth and height. So depth is the distance from the root node to any node, and then height is the distance from a node to the farthest leaf, right? And so we'll get into that. You'll know what all that means. And so balance. So a balanced tree keeps the height proportional it's a logarithm. And then an unbalanced tree. Well, an unbalanced tree is basically a linked list, right? Because there's no logarithmic, there's no reduction of the problem area, right? So you're just pushing everything to basically a linked list. You're not splitting it up. And so for construction, so there's this thing called the rules of binary search trees. And it has a left child rule and a right child rule, right? So the left child rule, that means that values smaller than the current node go to the left, and values larger than the current node go off to the right. Okay, so you'll see up here. It's a great example. Okay, so let's say that we've got a container of values. Okay, so we got 10, 5, 15, 3, 7, and 20 here. Okay, so if 10 goes in first, it's going to automatically be the root. 10 is going to go in first. It's going to be the root node. Everything is going to be compared to that root node, right? So 10 is going to go in first. Okay, 5 is less than 10, so it's shoveled off to the left. 15 is greater than 10. It doesn't replace the root. The greater value doesn't replace the root. It just goes to the right of it. All right. Then 3 comes in. 3 is less than 10. It's less than 5. So it goes to the left of 5. Once again, nothing is overwritten here, right? And then 7, well, 10 is smaller than 7, but it's greater than 5. So it goes to the right of 5. Okay? And then 15 is greater than 10, so it's pushed off to the right. And then 20 is greater than 15, and it just continues to the right of 10, to the right of 15. So, what I see people getting tripped up about is around the value sizes. They tend to kind of, you're just kind of used to day to day, you're just kind of used to larger values kind of overriding smaller values, but that doesn't happen here, right? Like there's very specific functionality around traversal, sorting, deletion, insertion. Everything is compared to the root in these things, unless there's a reason why you would want to replace the root explicitly. Okay. These rules, this whole idea of going to the left and to the right, this is very important because they ensure that searching for a value is efficient, right, and logarithmic time on average. And so because each comparison is eliminating half of the remaining tree. And so this is a rule of thumb of mine. You guys have probably heard me say this in other videos. But if the algorithm reduces the problem space at each step, think logarithmic time, right? And so that's just a rule of thumb to go by to sort of identify these time complexities quickly. And then so the advantages and disadvantages of these things. So binary trees, great at searching, inserting, and the deletion operations, right? They can also be dynamically resized, unlike arrays. However, though, man, once again, if there's no balance, it just turns into a linked list, and that's going to be, and so you lose that, right? So you're just going to be, that's just going to be linear time, and so it's just a linked list. So use cases, you've got binary search trees. So these are efficient searching. You can think about database indexing or like symbol tables in a compiler. Dynamic storage, managing an inventory where the size and the order of the data frequently change because it has that efficient insertion and deletion, right? And then file systems. I mean, obviously file systems are big O trees, and then expression trees, like I said, these represent mathematical expressions where each node is an operator or an operand, and it traverses the trees and it kicks off and it fires off these expressions, right? And so compilers use this to evaluate expressions, and then Huffman trees, which we've already talked about. Binary heaps, which are used to efficiently calculate shortest distance or smallest element. And then, decision trees, obviously, right? I mean, we're talking about, and this is used a lot in machine learning for classification task. And decision trees are used to analyze patterns, and so you can think of like a lot of, I've done fraud protection stuff, and so decision trees are pretty much at the core of any, or a fundamental data structure at the core of any fraud protection system. And then, okay, so we're going to do a little bit of a code run through. I just want to kind of show you guys the code at first. We're not going to, this isn't deep, as usual. That's what the code video is for. All right. So the node structure, so we're going to use our own specific type called a tree node to represent a single node in the tree. It's going to have a value. It's going to be generic, even though it's going to be generic, even though we're going to use just integers for ours. And then it contains pointers to optional left and right children. If you don't know what an option in a box is, we'll get to that in the code. Just creating optional pointers to memory, right? Pointers just contain memory addresses, right? That point to locations in memory. And then the tree structure. So the only thing that the actual binary tree holds, it just holds the root, right? And if it's none, the tree means the tree is empty. We have an add method. Remember, the code that I give you, it's not optimized. That's not the point. The point is that it's easy to reason about. It's easy to implement. It's easy to bring to mind, and it they're just, I think that these are efficient. These are very efficient for human understanding and memory. Okay, so that's the point of these. And then you can getting these implemented, and then you can start doing your optimization task. Getting these implemented is the tricky part. And so add just adds the first node as the root, and then it recursively inserts using our insert node function. Dude, this is so easy. Like, and it's the thing is, man, when you write code that's very easy to reason about, you have to balance verbosity and succinctness, right? And so this is not difficult. This is basic matching, and if you go through these theory sections and you listen to me go through the code, you're going to be able to just go step by step through these, and it's really just understanding and knowing the syntax of the language, right? In our case, we're using Rust, but I mean that's what it's about, right? So this is not, dude, once you see what we're doing here, it's nothing crazy. But yeah, so we have an add method. We have a search method, which checks if a value exists. This is also a core functionality. As you can see here, once again, it's just some matching, man, and it's a lot of the logic repeats because you're dealing with two. You're basically, for all intents and purposes, you're dealing with two. What's that word? Symmetric sides. Yeah, that's the word. You're dealing with two symmetric sides for the most part, right? And so so it's just matching and doing the same logic, dude. It's not bad. Now the delete method also is this also looks a little intimidating, but once again, man, this is just basic logic. It's not crazy. You're just kind of you're just catching the you're just catching all of the you're just catching all the angles, right? All the flows, and so and all the comparisons and everything. So this isn't crazy. If you truly understand the concept of the algorithm, you're going to get through this stuff no problem. And it really doesn't turn into memorization, guys. It doesn't. I mean, it really just, you basically talk your way through it like a script. That's what it turns into. This isn't memorization. And so that's it. So that's it, right? So you got to delete, you got to search, you got an add, and those are really the three functionalities that I think I would expect someone to be able to implement. So yeah, so that's it, guys. So if you have any questions about this stuff, hit me up. Help each other out in the comments. Ask respectable questions and you'll get respectable answers. Don't be an asshole. All right, and we'll see you in the next video. Cool.